Good afternoon, everyone. Today we are presenting a detailed tool-based study on Teneto. Teneto, a Python library developed for temporal network analysis within the broader field of network science. This presentation is part of the network science course at Indian Institute of Technology, Bhilai, and it has been prepared by Group 10 consisting of G. Banu Prakash, B. Haricharan Gaur, and me, K. Nitin. The motivation behind choosing Teneto is grounded in a key limitation of classical network analysis, meaning most real world systems evolve over time. Yet, traditional methods often treat networks as static objects. Our goal today is not merely to explain a software tool, but also to build conceptual understanding, explain why temporal networks are necessary, and show how Teneto supports such analysis in practice. We will begin with foundational concepts and gradually move towards advanced analysis and hands-on workflows. So, coming to the outline part, this slide presents the structure of our presentation, which includes subtopics like overview, what is a network, architecture or high level design, supported network types, wide temporal networks, core functionalities, scalability performance, strengths, and also like limitations, real world or research use cases, conclusions, and references also. Now we begin with an overview of Teneto and then revise fundamental network science concepts such as nodes, edges, degree, and adjacency matrices. We then move into the architectural design of Teneto, the types of networks it supports, and the motivation for choosing temporal networks. After establishing this foundation, we discuss Teneto's core functionalities, scalability and performance, strengths, limitations, real world applications, and conclude with key takeaways and references. This progression ensures that both theoretical understanding and practical usage are addressed systematically. So, coming to the tool overview, Teneto is a Python based network science library designed specifically for the analysis of temporal or time varying networks. In traditional network analysis, interactions are aggregated into a single static graph, while the simplifies analysis, it removes critical information about when interaction occurred. Teneto addresses this by allowing edges to be explicitly associated with time, enabling the study of dynamic connectivity patterns. The tool is widely used in domains such as social network analysis, which involves evolving interactions over time, biological networks, which include brain connectivity and neural communication, and information diffusion, like spreading of information or influence, and temporal networks, which like indicate time-stamped relations. Teneto is primarily aimed at researchers and students, and it prioritizes theoretical correctness and analytical depth over ease of use features like graphic interfaces. So, before continuing further, we now shift our focus to revisiting the fundamental concepts of network science that underpin Teneto's design. So, coming to the next part, what is a network? A network is a mathematical representation of a system composed of entities and the relationships between them. The entities are referred as a nodes and the relations are referred to as edges. This abstraction allows us to model complex systems such as social interactions, transportation systems, biological networks, and communication infrastructures in a unified manner. Network science studies how these structures behave, evolve, and influence processes such as information flow and robustness. So, in this figure, we can observe that these things are called as nodes, and these connecting paths are known as edges. We generally see this diagram in our daily, uh, we can say like passing of the network from router to the other devices. So here router is the main node, and these are the rest other nodes. And here is the edges which is carrying internet. That means information. Now we will go to the next part, nodes and edges. Nodes represent the fundamental entities of the system. Depending on the application, they may represent people, computers, sites, or brain regions. Edges represent interactions or relationships between these entities. In static networks, edges are assumed to exist continuously once present. However, in real world systems, interactions are often event based, occurring at specific times and then disappearing. Temporal network analysis treats edges as time-stamped events, which is a core idea implemented in Teneto. So, as we have discussed, like these are considered as nodes and these are considered as edges. So, for example, we have shown this image, but generally we can consider daily life examples like traffic network, or we can say that social like we can say that influence of a social media influencer, like we see in a daily life that one influencer is followed by our one of the follower, and he shares the information to us, and we like the content we follow him. So the sharing is considered as an edge, and the followers are considered as node. Now we move to the next part, that is degree of a node. So the degree of a node is the number of edges connected to it. In static networks, degree is a fixed value and is often used to identify important nodes or hubs. In temporal networks, degree becomes time dependent, meaning a node's importance can vary over time. This allows analysis of when nodes are influential rather than assuming constant influence. Now, if we try to calculate the degree of each nodes here, we can see that each node is having a degree of 1. Like we can assume, we can calculate degree by number of uh, edges passing from a node to the other node. Here one edge is passing, and from here, and we can see that highest degree is having to the central router, Wi-Fi router, which is passing the network to the all such devices. Like here we can see 1 2 3 4 5. Here the degree of the router is 5, and rest of them are having a degree of 1. Nodes with high degree are called hubs. So we can call this as a hub which is passing internet to every other device. So we can see that here the node is highly connected with rest of the nodes, and we can see that all other nodes are least connected with other devices. They're having only one connection, that is with the main router, which is a hub. Now we will know about the adjacency matrix. Networks can be represented using an adjacency matrix where each element indicates whether a pair of nodes is connected. This representation enables efficient computational analysis using matrix operations. Temporal networks extend this idea by using a sequence of adjacency matrices, one for each time step. Teneto is designed to handle and analyze such time revolved representations. So generally we are representing the adjacency matrix Aij is equal to 1 if nodes I and j are connected, 0 otherwise. So we can assume a matrix size of n into n where there are n nodes, and it can be used for a computational analysis. Here it is a adjacency matrix where we can indicate that here router is connected with laptop and printer. So 0 indicating not connected and 1 indicating connected. Having reviewed basic network concepts, we now move on to the architectural design of Teneto. Teneto is designed as modular Python library focused on temporal network analysis, meaning its components are separated into reusable modules. Teneto is a backend face tool. We do not have any graphical interpretation like other tools like Giphy and all have. It is built on the top of the Python scientific ecosystem. As discussed, it is a backend focused tool without a graphical user interface, allowing it to be integrated into research pipelines. The design philosophy explains simple data representations, reusable analysis modules, research oriented and extensible. This design emphasizes reproducibility, flexibility, and analytical rigor. Now we move to the next slide to discuss about the components and data flow. So generally, Teneto supports Python programming language. The core libraries involved in it are NumPy, NetworkX, Skype, or Matplotlib. Teneto leverages the Python scientific ecosystem, including, as discussed here, NumPy for numerical computation and NetworkX for graphics computation, graph representation, and obviously Matplotlib for showcasing of graphs and networks. It supports input formats such as timestamped edge lists and temporal adjacency matrices. Now, sorry, and output of the tool, we get temporal network measures, time resolved connectivity metrics, arrays, matrices, and plots. The output consists of time resolved metrics and plots that describe how networks evolve over time. We now examine the types of networks supported by Teneto. Teneto supports static, directed, undirected, weighted, temporal, and multi-layer networks. This flexibility allows it to be applied across multiple disciplines using a unified framework. So we come to the next slide. We now address the central motivation behind Teneto, the need for temporal networks. Most real-world networks are dynamic, meaning not static. Static representations ignore timing and ordering, which can lead to misleading conclusions. Temporal networks incorporate time explicitly, enabling analysis of causality, evolution, and dynamic processes. As we discussed, social interactions change over time. It is not fixed. Brain regions dynamically cooperate during tasks, and information spreads in specific temporal sequences. So, as we discussed, these are not static. Static networks generally fail to capture when interactions occur and the order of connections and obviously the evolution of network structure. Temporal networks explicitly incorporate time, enabling deeper and more realistic analysis. So next we will discuss what is a temporal network. A temporal network represents interactions as time-stamped events. A temporal network is a network representation where connections change over time. Static networks cannot capture as change in time, but Teneto as temporal networks can capture with change over time. Teneto ensures the capturing of temporal network, which will be further used for more analytics and more visualizations. This produces a sequence of network snapshots ordered in time. Such representations preserve critical temporal information lost in static graphs. So, in basic network representations, we have generally nodes which represent entities like people, cities, brain regions, etc. Edges represent interactions or relationships, whereas in temporal extension, each edge includes a timestamp and also has binary edges and weighted edges. As we can see that a basic network is with a fixed number of nodes and fixed number of edges. But whereas here edges evolve with a timestamp and change over a time. It is very difficult to capture, but Teneto ensures to capture the temporal network. This can be used for several advantages like to calculate changes in weather. Like we can observe that weather is not currently constant all over the time. It changes with type and season. So for such real world applications, Teneto is a really very good application. This results in a time ordered sequence of networks capturing how interactions evolve. So next we'll move to the next slide. Time varying connectivity. Time varying connectivity studies how interactions evolve over time. It is widely used in departments like neuroscience, cognitive science, and social network analysis. Teneto provides a unified framework for analyzing such systems. Time-varying connectivity refers to methods that analyze distributed interactions that evolve over time. Temporal network theory is one approach within this domain, focuses on time-stamped edges between nodes, and it is commonly used in, as discussed, the different departments, not only in neuroscience and cognitive science, but also different departments. Teneto bridges the gap, the temporal network theory, with time series based connectivity analysis. Now, next slide, I would like to show a visual example. Sorry. So this is a visual example where now in the first image we can see a static network where the number of nodes are fixed and edges represent the relationships, and these do not evolve with change over time and are difficult to capture. Here the relationships are fixed, whereas in temporal network we can see that there are more number of nodes and one node is having connection with many different other nodes, and we can see that in as here x-axis is represented time. So at starting here we can consider this node Blake is connected or having a relationship with Ashley. As time passing at t equal to 2, here earlier where Dylon or Cassie or Elliot are having no other relations, but in t equal to 2, Dylan is having a relationship with Ashley, with Cassie, and with Blake. So as time is evolving, we can observe here that there are different relationship patterns which are captured by using Teneto. Here, as discussing now, all edges are aggregated, ignoring when interactions are. So basically static is a fixed one, whereas temporal view, edges appear according to timestamps. We can see that t equal to 1, t equal to 2, t equal to 3, and obviously t equal to 4. Time varying connectivity captures when interactions occur, not just whether they occur. Now we'll move to the next slide. We now move into the Teneto's core functionalities. So, Teneto focuses on constructing temporal networks and computing temporal metrics such as temporal degree, efficiency, flexibility, and density. Teneto focuses on the analysis of temporal networks and time varying connectivity. Network construction, where we create temporal networks from time-stamped edge lists and along as discussed with time series data, and it also supports binary and weighted temporal networks. The temporal network metrics are basically temporal degree, temporal efficiency, network flexibility, volatility, and temporal density. Now, my other teammates will continue rest of the part. Thank you.
Thank you, Nitin, for explaining the idea of temporal networks and briefly introducing the core functionalities of Teneto. Hello everyone, I'm Haricharan and I will now explain these core functionalities in more detail. After that, I will talk about how Teneto analyzes results, its performance, strengths, limitations, practical considerations, and a use case. Teneto mainly focuses on analyzing temporal networks and time-varying connectivity. Unlike general network tools, Teneto is designed to answer one key question: how does a network change over time? To answer this, Teneto provides two main functionalities. First one is network construction and the other one is temporal network metrics. First, let us look at network construction. In real world systems, interactions do not happen continuously. They happen at specific moments in time. For example, people send messages at different times. Brain regions interact during specific tasks. Devices communicate at certain intervals. Teneto represents these interactions using time-stamped edges. When we write an edge as a tuple I, j, t, it means node I is interacted with node j at time t. If the interaction has weight or strength, we write I, j, t, w tuple. This representation keeps the time information which static networks usually lose. This is one of the main reasons why Teneto is useful. Teneto can also construct temporal networks from the time series data. For example, in neuroscience, signals are recorded from different brain regions over time. Teneto helps convert these signals into time varying connections. This allows researchers to understand and study how connectivity changes during different tasks. Once the temporal network is constructed, the next step is analysis. Teneto provides several temporal network metrics that helps us understand how the network behaves over time. First one is temporal degree. Temporal degree tells us how often a node is connected at different time steps. A node may be active at some times or inactive at others. Temporal degree captures this time-based behavior which static degree cannot. Temporal efficiency measures how easily information can move through the network while respecting time order. Even if a path exists, information cannot flow if the timing is wrong. So, this metric gives a more realistic view of communication. Network flexibility shows how frequently nodes change their connections. If nodes keep changing their neighbors, the network is highly flexible. This is very useful in studying neural networks in brain. Volatility measures how unstable the network is over time. Temporal density measures how many connections exist at each time step. Together, these metrics describe how dynamic or stable the network is. Analysis, scope, and limitations. After constructing the network and computing metrics, the next question is how we analyze these results. Teneto allows us analyze across time windows instead of treating the entire timeline as one block. This means we can divide time into smaller intervals and study the network step by step. This is important because many changes can happen gradually, not suddenly. Teneto also provides us summary statistics across time. These help us compare different time periods and identify stable and unstable phases. Another key feature is temporal null models. A null model is a randomized version of the original temporal network. Why is this important? Because not every pattern we see is meaningful. Some patterns appear just by chance. By comparing the real network with a null model, Teneto helps us check whether observed changes are statistically meaningful or not. For visualization, Teneto supports basic plots using matplotlib such as how metrics change over time. Advanced visualizations require external libraries. It is also important to note that Teneto focuses on analysis only. It does not simulate processes like information spreading or epidemics, and there is no graphical user interface. It is completely focused on analysis, not on network generation. Now let us talk about scalability and performance. Teneto is mainly designed for research scale networks, not very large industrial networks. Most use cases in these networks involve networks with tens, hundreds, or a few thousands of nodes. This is common in academic research, especially in neuroscience and social studies. Performance in Teneto depends actually on number of nodes, number of time steps it taken, density of temporal connections. As these increase, computation time and memory usage also increases. Teneto is built on NumPy, which allows efficient numerical computation. However, it is not designed for massive real-time systems. Temporal networks usually require more memory than static networks. This is because instead of storing one network, we store many networks across time. If time resolution is very fine, memory usage increases quickly. Teneto does not provide built-in GPU or parallel computing support, so computations run on the CPU. For most research datasets, this is sufficient, but for extremely large datasets, performance can become a limitation. One strong point is that Teneto supports statistical validation, which is more important than raw speed in research, as it supports temporal null models and it enables comparison against randomized temporal networks. Now let us discuss the strengths and uses of Teneto. What Teneto does best is Teneto specializes the analysis of temporal networks. It captures the network structure, evolves over time, not just a single snapshot. It bridges the gap between static network theory and time varying connectivity. This makes it very suitable for real world systems. Teneto has several unique features. It has native support for time-stamped edges, where time is a core part of the network. It provides temporal network metrics that are not available in standard tools. Teneto also integrates network science with time series analysis, which is especially useful in neuroscience. Why researchers prefer Teneto? Teneto actually is designed specifically for scientific research. It is widely used in network neuroscience and cognitive science. Teneto is open source and extensible, meaning researchers can modify and extend it for new problems. Why Teneto is preferred in research? Teneto enables analysis that static networks that cannot capture. Static networks can only tell us whether connections exist. Teneto tells us when and how connections change. Teneto also provides temporal null models for statistical validation. It is well documented and has strong theoretical grounding. Teneto supports reproducible research workflows, meaning results can be repeated and verified. Overall, Teneto allows researchers to move from asking whether the connection exists to when and how connections change. There are a few limitations for Teneto tool. Let us discuss them now. Like any research tool, Teneto also has several limitations. It has a learning curve, especially for beginners. Understanding temporal network theory is important to use it properly. Teneto is not optimized for very large networks. Visualization options are limited, and dense temporal networks can consume a lot of memory. These are all several practical challenges that can be faced while using Teneto, as it has several missing features in it with no built-in simulation models, limited advanced visualization support. In practice, Teneto works best as a part of research workflow, not as a standalone tool. It works well with NetworkX for graph handling, Matplotlib for visualization. Teneto focuses more on analytical accuracy than speed or user interface. So, it is ideal when we want to carefully study how networks change over time. Now, let us look at a use case of Teneto. Consider a temporal network where nodes represent people or brain regions, edges represent time-stamped interactions. Using Teneto, we can construct the temporal network, compute the temporal metrics of that network, and analyze how metrics can change over time. This helps us identify important nodes at different times and stable periods and periods of high activity. If we convert this to a static network, we lose this information. This clearly shows why Teneto is useful. With this, I have explained the core functionalities, analysis scope, performance, strength, limitations, practical considerations, and a use case of Teneto. Next, Bhanu will explain the workflow demonstration where he will practically show how Teneto is used step by step.
Yeah, thank you, Haricharan. Yeah, I will take up from here. So, as we are discussing about the Teneto, the tool used for the network science analysis. So, to the next part. So, we go with the hands-on session, we can say that, and a little bit of real-world examples. Try how to use the Teneto in actual using code, right? Let's see it. So, let's go to the examples. So my friend Haricharan I talked how what is the use case of Teneto in real world examples in research. So we go further. So I guess you guys know this movie called Tenet. So it's a very fascinating sci-fi movie, although where it actually runs in parallel with the past and future. So why I'm actually talking about this movie is this has the same uh, similarity with the tool Teneto because this tool actually deals with the temporal networks, which actually involves the time series, how the graph changes or the network changes over the time, given timestamps, right? So yeah, just to have the nuance of the tool, so I just added here. So let's get into the tutorial. So what I'm about to show is we can install Teneto package in our Ubuntu or any OS. But for simplicity, we use Google Colab for simplicity to understand. So what we do is just generate a random network and try to use Teneto on that, and let's see what we get from the network, right? So let's get into that. So before that, I would like to show you these resources about Teneto, where there is a detailed documentation for this tool. So the image here, so itself says that like how the graph changes on the given timestamps. So there may be new edges, or there may be deletion of the previous edges, expansion of graph, or the graph size may decrease, or number of degrees may increase. So it is uncertain that you cannot tell a particular thing happens in the given timestamp. So we just use this tool to gather the main thing, like the underlying similarity or a factor that actually makes us to analyze the network better, right? So let's get to the what is temporal network. So I think this actually discussed before with of by my friends Nitin and Haricharan. So I would like to ignore like for this thing and just move on with the next thing. So we have this thing. So we knew, actually already knew about temporal networks and what is Teneto basically. So let's get into the thing. So coming to network science, right? So we are actually eager to know about the network, what conclusions we might get from the network, so we can make decisions. We can make the optimal decisions, right? So you can take any given network like the social media network like Instagram, Facebook. So right, or you can have a school friends network or handshake network in your campus, right? There are vast networks you can talk about it, and so mainly we are talking about the time series dependent networks called as temporal networks. So these measures, like the centrality measures, actually helps us to finding the important nodes. So what we do by finding the important nodes, because we might uh, make it as a hub, the main point, or we can find out the single node can be, if it actually dies, so overall network will be affected, right? So we need to minimize the effect and maximize the profit, right? This is the actual thing of us. So let's get into main thing. So we have these measures in the temporal network also using Teneto, right? So the degree centrality, we say betweenness centrality, closeness centrality, and degree centrality of uh, community vector, right? And temporal efficiency, like how it reflects one on a network when we compute all these things like reachability, latency, volatility, all those things, right? So this is the main resources that I could talk about, because it includes everything about Teneto, right? So coming to the workflow, like how you actually use this Teneto to take the do the analysis on the network. So here I want to add this thing, right? So as when you see a network, so you just can't actually go with the random decision, right? But you somewhat you can guess something like similarity or some pattern you can guess in the network. But coming to these temporal networks specifically, so that depends on time. So it is like you cannot guess it, right? So that is the main thing. So workflow is like you should let's generate a random network, temporal network, and we see how we need to initialize the thing of like the network, and how we move further to get our analysis on the created graph using Teneto. So let's create, it's actually the code here. So you just use this code to run, and as I said earlier, so we are using the Google Colab. We can use the Ubuntu or a terminal to install Teneto, but we need Python environment previously, so that it can actually run it on Python, right? Python based too, like a package, not it doesn't have any separate software or graphical interface that you can actually see in real time changes, right? Just particular piece of codes, functions that actually make use of. That's enough for the Teneto. So here you can, if you see clearly, so you can see that how Teneto nodes, like the graph is created, like the node name, and you should add node. So you can add node in the temporal network, and nodes, you can see the nodes and function temporal network. And graph, it says like it is root, and you add the another node name, generate network, and degree, add nodes degree. So now the graph became, so the create temporal network is a node, but actually is root now. So then there are links, like it is a, so central temporal network, and then has link to the create temporal network, then to link to the generate network. So it is a binary undirected graph, we can say that, because there is no weights for now. So there are only 0 or 1. If there is an edge, it is 1. If there is no edge, it is 0, as we see in that adjacency matrix, as discussed before by my friend Nitin. So I think you are all actually familiar with the basics of the network, like the graph, edges, nodes, degrees, all this. So we are not gonna go into that now. So yes, so here uh, the Teneto actually given the example how to use Teneto. So Teneto has the built-in functions to generate random networks. Like it uses a random binomial function, creates a temporal network. I will show you soon, but let's go into detail in that. So if we see the modules, so there are some classes like Teneto have these packages like these import like the packages here. So the classes, like what are the temporal class, how we actually use temporal network when you initialize a network with temporal network, like change it to the temporal network. So what type of parameters do you need? So you should see from here, and add edge, binarize, df to array, like data frame to the array representation, drop an edge, generate network from array. So all these things like very detailedly mentioned here. So I'm not gonna get into detail in that because we have some time limit factor because the video is very long. So as we discussed before, these community measures like persistence, something like if when you actually deal with the bigger networks, right, it make you some, it will give you some sense of okay, this is the parameters we should need to consider for network to analyze, right? So yeah, so coming to the generate network, so if you given a randomized number, you want a random graph or network to be generated, you can use these both functions here from the package, that is random binomial. So because it is random, so it uses a binomial distribution. So coming to the main thing is that true probabilities, size, number of nodes, probability. Probability means like when you create a network, right, with some nodes, like you want to add the edges. So if it is a random network, how you decide to add a network between two nodes, right? So there is a probability. You can follow that probability to add a edge between any two random nodes. Or you can, as we are discussing about the temporal network, so means it changes through time. So there may be addition of edges or the deletion of edges. So there will be two probabilities, like the birth and the death of an edge, because the birth represents what is probability, or by which probability I should add an edge between the two nodes, and the death probability is the probability of remaining of the edge while I want to delete some subgraph or some edges in the graph while given timestamps. So these are two things. So net type you will like the like BU means binary undirected graph, BD means binary directed graph which have the direction between two nodes as the edges, and some randomized, which is a random seed, like just have a random number to actually generate the thing. So this is just like the example. So how we use NumPy and Matplotlib because we need to plot the graph, the changes on timestamp, right? So here, if you see closely here, so it actually uses the NumPy to randomize the graph, the number, and we have given the number of nodes as n, 5, and time stamps or time points as 10, and birth rate is 0.25. So here only birth rate is given, like the probability by which I should add an edge between given randomly two nodes, right? So use this function called as teneto.generate network and use random binomial format. So this is the format how you use the function, and then we use the matplotlib to plot this thing. So here you can see in this example, so how the edges have been added and here have been removed and then added and removed is completely random, right? So when we add the depth rate, so the example says like below we create a network with 5 nodes and 10 time points. Edges have a 25% chance to appear and have a 75% chance to remain. So yeah, that's actually said before. So here when you use this, both probabilities of birth and death of an edge, we get this edge or this network, right? So given timestamps are 10, having 5 nodes. So this is the graph, this is the network. So how you can get the analysis of this network? What is a pattern lying under this network? So we need to use more functions and according to your requirement, what is your objective to get the information from the given network? It depends on that mostly. I think yeah. Let's get back to the main thing and yeah, the most important thing is the network measures. Like these are the most crucial part of analysis. Like we want these parameters to judge a network, like what happening in the network, what actually it is telling us, what is the pattern underlying it in the network, right? So temporal degree centrality, given temporal degree of a network. So what is a like temporal degree of a network on a given at a given timestamp, right? You can say that. So closure centrality, so we efficiency, bitwiness centrality, all this thing, right? Participation coefficient. So all these things come into the consideration of network measures. So when you come to the plot, so Teneto gives you three types of plots: slice plot, circle plot, graphlet stack plot. So slice plot just tells us like the given timestamp, right? Just have to slice like the previous graph I shown you before, right? So given timestamp, what is the current state of the given network, like which edges are there, and later the next timestamp, which are added and which are deleted. So this thing can be shown in the slice plot. So you can see here the same image, but the given time as a year and the nodes as persons here. So they might the friendship, maybe friendship or something like that, the relationship between the edges between two nodes. So circle plot is another circle plot. So just the same type of, but this actually uses a circle plot. Like the visualization is different, like how you see a network is different. Like if you want to have a different type of objective on the network, so you can use as per your requirement, and this graph is stock. So let's get back to that, and we have the time series, the main thing. So you just have to just try all these things and just on a given graph, and just you can just Get it what I'm trying to say? Okay, yeah, I think you guys are waiting for the main thing, like the actual application of the Tenet. So we use Colab, and let's get into that. So here you can see the we can use Teneto and we can install using pip in the thing. So later we use the NumPy and pandas as well and matplotlib to plot our graphs or networks. So temporal graphs are those graphs whose connections change over time, or it will actually gives a dynamic view of relations, how relations change over time. Like example, we can take the Instagram follower list. So one time you might follow one person, and later you will change your decision and you want to unfollow them. Then it actually changes the graph or the network of the Instagram, right? All these things. So these are the probabilities scenarios, as I told, exist, P doesn't exist, 1 minus P. So remains after random deletion, Q, and exist and remains P times Q. So let's jump into the actual Teneto application of a random network, which is a temporal network. So you can see there are 6 nodes here and given 12 timestamps when we have given the two rates called as birth rate and death rate. And also let's go to the, so we use the random binomial model and size, probability, and contact, like it is what actually it tells. So the contacts between nodes, right? So how we can give a name to that relationship, like that. And we actually using the binary undeclared graph, so there are no weights here. So this is a sample of temporal edges of the 6 nodes. So we can, if you can analyze this given random network of temporal network, we can get this graph on given timestamps. So at first timestamp, there are no edges. At 2, there are 2 edges. At 3, there are 3 edges. So as well, so when come to the 12th timestamp, so edges have been added and as well deleted. So it is uncertain, like actually cannot guess the thing behind this temporal network. So this is called as slice plot, as we discussed before. So as I showed you in the docs, we have this temporal network class. So like an object, you can use object to initialize into the temporal network very efficiently. So just give the edge list, like we have the contacts as the relationship. So what is edges, by the way? So it is nothing but it is a relationship between 2 nodes. That might be anything. So here we are using about contacts as a name for the relationship. So we are getting contacts as edge list from the net, actually generated before using random binomial form, and then node labels and giving a node I for that. So we just try to use the temporal network object and just push this data into that. Like the given data is in form of uh, 2D array. So similarly, just push the data into that. We will get the temporal network edge list. So we have the ij as the edges, like the nodes, sorry, and the timestamps, right? So yeah, coming to the main important thing, measures. So here you can see we have this graph of 6 nodes and 12 timestamps, right? So we use this temporal degree centrality, so to measure that. So simply we use this function to get the result. So there is straight away forward. And coming to the betweenness centrality. So when we try to compute the betweenness centrality, right? So we have many methods. So the most efficient till now, what actually I studied is like firstly we used to compute the dependency of a node, right, on the other node. Like it actually includes the concepts of shortest path, number of shortest path, right? So you can remember if from the concept of network science in deep. So given a node, right, and the root node. So how the given node is dependent on the root node. So number of shortest path passing through it, and children of the node actually has a role in it. So I don't want to make you complicate. So yeah, it's similar concept in that. So you used to compute the witness and validity using that dependency thing. So it actually takes a lot of time to compute this betweenness and duality. So I just use a small graph using the four nodes and four timestamps, right? So probabilities and given here. So for the temporal betweenness and duality, so it is zero. So might be zero because there is no actual type of relationship between them. It's a very small network. So closeness and duality is a different measure. So how each node is close to the every other node, the factor, the thing. So given the value is this, and yeah, if you have a CSV file like yeah, have many columns, right? Like the columns of the in format of IJT, like the edge, like the nodes, node A, node B, and the timestamp when they have this edge between them. So it can be used also. You just use a temporal object, this thing. I couldn't actually show this thing because yeah, due to some issues. And let's go to the real world application. So this is what all about, right? When you have the network in your hand, you try to use these tools and get the thing out of it. So coming to the temporal networks, we have similar networks in the real life data. So here this data includes of a email type of data. So it is called as email EU core temporal dataset. You can find this in the given link. All those links and files and this PPT and this IPYNB file, I will put link below the video in the description. So do check it out. So we use this file and it's actually a huge file, right? So when you're trying to so there is this concept called as sparse networks in network science, right? So when you're actually dealing with many measures on the network, so in real life you just find many nodes, huge nodes, like million nodes. But coming to the edges, they are very sparse, right? So this is one of the key thing in the network science. So as the given data set, like the data set I chose, so it has huge nodes. So I just wanted to print the first 10 nodes, right? The data set, right? The IJT, the timestamps INJ here. So we used to, so the number of interactions, like it is called as how many interactions, like how many edges are there between INJ, right? All those things, and convert this thing like the data frame format to temporal network format. We just try to do it, and similarly we'll get the thing. So this is the data set in the column format, and now we have changed it into a temporal network having the ij and t, right? That's fine. So just wanted to print some because it is a very huge network, so it's very difficult to show all these things here. So similarly, we used to plot this network like using slices. Yeah. So what I done is here. So we have this huge network, Tenet real. So I just wanted to pick a small part of the main network and just use a small subgraph or sub network in it and just try to analyze it because it is very huge to show here. So just use the small part of it and just try something on it. So we just use tnet small on the df small. We just plot the slices, right? So you can get this right. There are some nodes randomly select 10 nodes, the first 10 steps. So how the each node actually evolving, right? The new nodes are added only. Like from this, you can say that there's only one edge is actually the new edge is introduced and the one edge is deleted as the previous one. You can see only one edge is coming and the previous edge is getting deleted. So overall the nodes, it is a random of the showing of the first like the 10 step timestamps here. So it may be very huge. So I just need to show some of them here. So as we know, we again want to know the network metrics, like the network measures, like the centrality measures per se. So degree, we can have the temporal degree centrality. So I have this small network of only some nodes. So it has node 2, node 42. So we randomly pick some node and just show it here. So there is this thing called temporal efficiency. Like when we try to look about this temporal efficiency, right? So you can see it here. Temporal efficiency. What is temporal efficiency here? Yeah. So temporal efficiency means you have the efficiency estimate. So what I how the temporal connection is changing on the network all the time due time. So it is a temporal efficiency, you can say that, and then coming to the time series. So how frequently a node changes its activity, right? Right. Given timestamp, it may have the highest degree sometimes. Sometimes it has the lowest degree. So the parameters, the network measures change at each timestamp. So you need to generate the each measures at given timestamp to get the thing out of it, the pattern underlying in it. So yeah, it is very difficult to actually analyze a temporal network for sure. So for the given network, so if you say as we are dealing with the contact relationship between the school data for say, so I have taken the thing here as a tnet. If I say that tnet real, if it is a real one, so I think it takes time to reconnect the thing. Yeah. So for here, it has the given timestamp. So contacts are 3. So yeah, I think the real network is not defined here. So just remain with that same. Okay, I think this is a race correct thing. It's no problem. So I think I actually gave you the application of Teneto, how we use, how we get the data, how we use the networks from the real world scenarios and apply them, and to get the underlying pattern in it. So when you deal with this temporal network type of data, use Teneto for sure, but it is not completely, we can say that completely not fixed to this. So we have input given a network, connection using timestamp edges, right? Time resolved network measures, plots and numerical results, and we can interpret it, interpret that there are like the relationship between the networks or the edges or the nodes, the given temporal time. So we have these timestamps like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So when you want to relationship between the 2 and 5 timestamps, so you can use that metric also. How what is the changes that it reflected in the given 2 timestamps or different between the 2 given timestamps or multiple timestamps. All right, this thing you can get out of it. So coming to the conclusion of this whole tool presentation, so networks type of depend on timestamps called as temporal networks captures how the edges changes over time. So it's very dynamic in change and very specific. And Teneto is specialized in this particular thing to get the pattern. So I think till now, you just got this into your head like when to use the Teneto, right? Like while the network is changing, it is dynamic, it is time dependent, and time varying patterns are there, right? So it actually comes between the static network theory and the real world dynamic systems or networks. So Tenedo can be used in there. So yeah, oh I thank our instructor Risharanjan sir and to and TH for giving this opportunity to represent or talk about this tool, which is very important in network science analysis. So I hope you guys enjoyed this session and hope you got what you actually needed. And yeah, that's it. And thank you. Have a nice day.